Good afternoon, everyone. We're going to start up again. Now we're moving on to the modeling stock structure session, and Aaron's going to be the keynote. We don't have a commenter. And after that, we'll have half an hour of discussion. We had a workshop for 2.5 days before the CAPAM workshop on spatial stock assessment modeling, and so some of the information from that will be quite relevant to this presentation, and a lot of those participants from that meeting will be here, so I'm looking forward to some good discussion. Also, Laura found this nice looking USB cable. It's really nice. It's yours, Simon?
All right, so we're good to go. Yeah, thanks everybody. Yeah, so I'm going to be talking about spatial structure. We got some co-authors on this talk listed here, which I'd like to thank, as well as part of this talk will be summarizing some of the things we talked about at the spatial simulation experiment workshop that many of you were involved in. So really all of you should be on here as acknowledgement, so I'm going to say that right off the bat. As well as, some of these thoughts and topics I'm going to bring up started way back in 2015 when there was a NOAA-NIWA workshop here in Wellington. Pamela was part of that, so I got to acknowledge her, as well as the late great Terry Quinn. So there's really a whole bunch, and all the CAPAM workshops and things like that of kind of momentum that has gone into some of the thoughts that I'll present. In terms of an outline, just going to step through a little bit quickly some of the needs for spatial structure, just try to be comprehensive there. And then, as I mentioned, go through the simulation experiment, because I think the idea of that and some of the results, but really more so using that as a kind of a case example of some of the things we need to do more broadly. And then end with some pragmatic guidance for implementing spatial models, some of which will apply to Tuna, and then some of it which is in a more general sense. So this is all really kind of towards thinking about best practices. It's certainly not anything set in stone. So just keep that in mind as we go forward. And this whole idea of developing best practices or practices for spatial models and modeling has gained a lot of momentum recently. There's these key papers here that I've listed, as well as the Moore et al., which we just heard about. They're specific to Tuna, and then the spatial simulation experiment as well. So all of these kind of have been formulating and building upon each other as we start to think about best practices. So again, certainly this isn't solely my thoughts, it's a compendium of thoughts over the last decades. I put this up there for general idea that we think of spatial structure a lot. This is mostly assessments. There's some of them that are management related boundaries. And the point here is I just want to say that they're important for highly migratory species as well as others. But if you look at these lines, these are all human constructs, right? Not very often do these lines always line up with strictly the biology. And in practice, we kind of have to integrate both of them because fisheries are clearly managed, not always necessarily for the fish themselves, but the human interaction with those stocks. And so we have lots of different examples. Each always have different objectives, and those are important to consider when we think about defining boundaries, thinking about linkages, and so on and so forth. All right, so going right into spatial structure. Why do we care about space? There's a whole bunch of reasons here. Of course, the first one that comes to mind is biocomplexity, ensuring we have population resilience and stability, also addressing fine scale dynamics. It can be biological processes or to other things, including even socioeconomics, fleet dynamics, things like that. Improve information content from data. So utilize the data at the scale it's collected. That's been improving, even noting lats and longs and things like that where samples are taken. And then also incorporate alternative or perhaps thus far underutilized data. We've been talking about closed kin mark recapture, genomics. There's a whole long list of things that are gaining momentum in that respect as well. Also, I think often overlooked is the reflecting, finer scale models reflect stakeholder observations, which goes a long way in a management procedure context for getting buy-in and things like that, as well as better incorporating ecological knowledge. And one of the reasons that I personally like to think about spatial models is that it explicitly makes you think about the assumptions that go into your model that you'd otherwise not think about if you just were aggregating over not a larger area and just looking at non-spatial models. And this can become important when we think about spatial management, like marine protected areas. Relevance in the news lately is the 2023 High Seas Treaty. So I suspect we're going to hear more and more about that, as well as climate change, species redistribution, and things like that from changes in large-scale oceanographics and environmental linkages. When we think about some of the things that drive population structure, we can look back at almost every topic we've talked about so far this week, and they all have a spatial component. In particular, density dependence and productivity is important. And here I'm kind of listing off some of the key drivers that when present, might really lead you down the path of looking further into the assumptions of a spatial model. So productivity, the amount of reproductive mixing, of course, connectivity through movement or other mechanisms, spatial variation in biological parameters, but also spatial fishing patterns. All of these can kind of interact to formulate different hypotheses about population structure, from a single population to a single population but with demographic heterogeneity, to metapopulations and so on and so forth with increasing complexity. So one of the things that we have been thinking about recently, and this is in a paper that Dan, myself, and Steve Cadron have put together, was out of the fall CAPAM meeting. And it's some of the decision points that we need to think about, both in terms of moving from a non-spatial to a spatial model, but also revisiting current assumptions. And so I'm not going to go through all these, but obviously the form of population structure is really important. The temporal structure, the resolution. We talked a little bit about fine scale spatiotemporal models and how those interact with larger scale assessment area models. Fleet structure, that's going to come back in a few minutes when I talk about the spatial experiment. But of course, that's important. Recruitment dynamics, initial distributions and scaling among regions, dispersal, all the sorts of different life stages. Of course, movement is always a big one, and the multiple ways in which that can manifest. And then demographic variation from life history, growth, fecundity, you name it, across our population. And I should have started this, that I'm kind of already starting from the standpoint of a stock has already been identified. And so I'm not getting into the details that were already discussed earlier, but just for reference, I'm already kind of assuming that that has been done, and now we're thinking within that stock. And so this table is great. There's a lot of high-level compilation here, but really, what about in practice? And so that's where we, at least one of the reasons why we have been working on this experiment over the last couple of years, and then had a great discussion over the last couple of days preceding this meeting. So just a little background for those that weren't there. The simulation experiment, kind of the goals of it were to compare how people went about model building, especially spatial models, what kind of decision points they came across, they had to wrestle with, make decisions about. Then look at also comparisons to an operating model, the truth of that operating model, both not just in terms of individual decisions, but also in terms of general approaches like areas as fleets versus a single model versus multi-area models, things like that. And then really to come away with lessons learned. And I'll discuss today a few of those, but this is clearly very preliminary. We just had our discussions the other day. So the formulation of those results are going to be ongoing, but I can give you a little bit of an overview that I think will help with discussions here. So we did build an operating model in the SPM environment. Don't know why it's doing that. And that operating model really kind of tracked fine scale population dynamics, which then we could build and simulate data sets from. We did that for two species, yellowfin and toothfish. Today, since this is tuna, I'll just be focusing on the yellowfin tuna example. And then we had a bunch of teams take that data and create estimation models. So we had 9 different teams looking at different approaches, and each one of those presented this last week on what they've done so far. The study design itself included 3 main objectives. The first one is about those decisions I was talking about. So we have our simulated data set, and then we actually created 100 of those simulated data sets. And as folks were building kind of their base model using one of those data sets, they documented their decisions. And so that was the first objective. So we did that for a single area model, and then data sets that were out to 4 areas. And this is for the Indian Ocean yellowfin tuna assessment, or based upon that in that area. So the analysis teams went ahead and did that, and then they built their estimation models and ran those. And we are currently comparing those models, the different approaches they took, non-spatial and spatial. And then we're looking at objective 3, kind of a cross-platform comparison, and trying to learn some things about the whole process of building and using spatial models. In summary, kind of the configurations that were explored, all groups developed a single strata model first. And some groups developed areas as fleets models. It was interesting, one of the groups included a new or newish approach that used regression tree analysis to actually identify the fleets in that areas as fleets. Typically, we do that a little bit more ad hoc based on management boundaries or fleets in particular areas. Without really thinking hard about parsimony in that respect. So this type of analysis looks at identifying those fleet structures in the best way possible, the most informative anyway. Many groups also developed spatially explicit assessments, including the use of tagging data. A couple of groups used more simpler models as developmental tools, kind of as decision points along the way to test some of their early on assumptions, to see if they're getting things relatively in the right direction before adding complexity. Most, if not all, the groups developed sensitivity runs, did some alternative parameterizations, alternative models to hone in on their general approach. Of interest, though, was the different approach that people use for diagnostics. I've got a list here of a whole bunch of different ones. I think it was pretty common that folks looked at residual patterns and fits to data, but there was also folks that did runs tests, used information theory, like AIC, likelihood profiles, et cetera, et cetera. So there was quite a array of differences in which people used to help guide their decisions. And that in and of itself is pretty interesting. In terms of the discussion, and this is just a subset, there was a high resolution data analysis was noted as good practice. And so this includes the specification of fleets for spatially implicit approaches. Novel data and the use of that was noted as important, especially for movement and identifying the form of population structure. And some of those data types were listed. It was pretty unanimous, the idea of starting simple and slowly adding complexity during the model development phase. Spatial model advancements, there, when we start thinking about things like adding random effects to try to counter the expansion of parameters when you go in the dimension of space, and other types of things that can help with movement, like preference functions, rather than a factorial array of parameters across all and every spatial connection. Reproducibility and the support of community of users to learn from was noted as important. Robust diagnostic tools, also a tendency to focus on fleet structure and movement for tunas in particular, whereas population structure was more of a focus for demersal species. So just given the nature of the data for tuna, fleet structure and movement spent a lot of time on that. And then we also looked at specific platforms, limitations and improvements. You may have noticed on that set of teams, we had a bunch of different software platforms that were used. And each one, while built with the same kind of output in mind, have different assumptions associated with them and things like that. Oh, and I did want to mention in terms of ocean-based and tagging, it was across all teams that tag mixing really is a tough one. It is a pain in the ass, but it is something that we have to grapple with. There was unanimity in that one. In terms of results, model comparisons, I'm just going to be a little bit quick here, just to state a few things, because this is certainly preliminary. In this figure here, we have the operating model, which is the orange coming across here, and this is for an aggregate model, so across aggregated SSB. And what we have is the solid lines are single area models, and the dashed lines are spatial models. And there's different types here in terms of areas as fleets, and then the spatial versus single area. And what you can just really see is a couple things. One is the spatial models tended to have a higher estimate of biomass than the single area models, and we're looking into that. Also, you can see differences among the different estimation models in terms of scale. So there was clearly some variability in scale. When we look at depletion, it's the same type of figure. You can see that while they all tracked each other pretty well, once you standardized by that initial biomass, the depletion trend was a lot more similar. I mean, we're talking about variability across every single model from 0.7 to 0.4. So still some variation there, but they tracked pretty well. And then when we looked spatially, this is where some really interesting results started to come out. We saw some really big differences between the operating model, and again, this is a fine scale operating model that uses preference functions and things like that to force movement. We saw some really interesting differences between the estimation models, where in some regions, like region 1 here and region 2, we saw a positive bias, and in other regions we saw a negative bias. So one of the next steps we're going to do is to really kind of tease out some of those biases. If you squint on those first pages, we're getting pretty consistent results across all these different estimation models in terms of depletion and trends, but we're seeing differences among them and against the operating model, the truth, when we go into the regions or the spatial, when you dive into the spatial differences. So we want to tease out some of those discrepancies that appear to be due to movement and recruitment, but in particular the disproportionate fishing mortality to biomass, kind of this regional scaling of CPUEs, we think is a big reason why we're seeing some of those differences. So in other words, it's a simulated data based on a real example. and those types of realities can arise, and this is a good example of what can happen in those cases. And then we'll put in, we'll improve the data and kind of see how those things connect, and that's kind of the next step for the next couple of weeks for some of us. Also, the fine scale operating model for testing or expansion to other geographic footprints we heard was a priority, or on a wish list anyways. So that would be the idea of using something like SPM and imposing it, say, in the Western Central Pacific area, ICAT, et cetera, to other areas, because there's seemed like unanimous support that tools like this, like the simulation experiment, fine scale ones, especially the operating model doesn't mimic the estimation model at all, is really important for having a base to evaluate all sorts of different things, and then you could imagine flow-ons to full closed loop simulations, management procedure evaluations, and so on. And then we are going to have a couple of manuscripts that come out of this work as well. And lastly, I'm doing okay on time, a little bit of guidance. There's all sorts of different choices that we have when building spatial models. And this spans from the data availability, the particular model framework and parameterizations that we choose. Also, there's drivers such as heterogeneity, ID, and sources of heterogeneity and connectivity. And then there's constructs, when we think about things like management, biology, political, et cetera, boundaries and things like that, that drive some of these decisions. And really, I think what we're advocating for is the attempt to determine minimally complex models that acknowledge the main drivers of spatial dynamics. We're not going to be, at least initially, able to get all of them, but to start with the main drivers first and then add complexity as data allows. And so when we think about all these different approaches, we put together this figure, and basically it's saying, analytical approaches that tend to be simpler and have less data often are empirical, and the complexity of the model choice often increases with data. And when we think about Tuna assessments, right now we're using single area models. There's areas as fleets approaches, and there's spatially explicit approaches. And the point of this figure is to really show there's a whole bunch more in there. There's really a continuum of approaches, and I think that there's some opportunity there, and I'll mention a little bit more about this in a few minutes, to really increase our knowledge and build things in our toolbox that help us determine some of these difficult decisions. Here's more of a written out statement of what I was just talking about. The three in the boxes are what was the three primary things done in the spatial simulation experiment. But again, just to show that there's a continuum of approaches here. And I put this in here so that when you looked at it later, you could dive into the details. Also, in terms of future needs, this idea of maximizing resources is really an important one. And primarily, I think that comes from reproducible workflows and iteratively developing, those complexities as we test those and determine that they are well enough designed and tested to be put into operational assessments. This idea really improves the ability to share code and co-develop models to maximize our resources. Use the collaboration in the communities that we have. I think the spatial simulation experiment is a good example of that. And then utilize advances. I think there's a big increase over the last 10 years in the reduction of runtimes and the tools we have to try to reduce runtimes. So these larger, more fine scale assessments, even as operating models or conditioning operating models, we're being able to overcome those with computing capabilities. And then just in terms of best practice, we think it should include stepwise progress towards complexities as appropriate. and that development is not an all or one type of situation, it's iterative. In terms of recommendations, I think we want to refine best practices as examples increase. When you look around the room in here, the folks that are doing spatial assessments are largely come from the Tuna world still. There's growing examples elsewhere, but there's still not a ton of them. So we want to refine best practices as those examples increase. I think we can improve conceptual models and hypotheses as we start using new data, methods further develop, and mechanistic relationships arise, especially in as they relate to oceanography and the environment. I think also there's a big opportunity to include hybrid models in our collective repertoire. This paper over here by Jim Thorson and others is an example of that, and I think this has come up a couple of times. But the idea is integrating finer scale information across all sorts of data types, along with stock assessment, the broader scale stock assessment boundaries we have. And I think one of the things we can do is link those, like in this paper, but also keep them separate in some cases too. If our movement isn't perfectly defined, we may end up sticking with a one area model, but the fine scale spatiotemporal models, even if it's not directly in your assessment model, can inform you about worries about local depletion, about fleet dynamics and things like that. Of course, tagging data, I agree with everything that's been said. It is still needed. And best practices for tagging design is probably something that we could put on a future CAPAM. But also, integrating some of the other data sources that are complementary that we've talked about already. Another big one that comes up is defining spatial reference points. I think we don't have very many examples of that, and that's definitely an area of future research. All right, and my final slide here is just some final points. One of the things through simulations that we've learned is that getting the form of your spatial structure correct can be more critical than ignoring it altogether. So in other words, if you don't have at least some idea of the connectivity, the movement, if it's ontogenetic, if it's source sink, and you get that wrong, you're probably going to end up in a worse place bias-wise than if you just ignored it. So in other words, it's important to have spatial structure, but you want to do it in the correct fashion. Resolving movement recruitment confounding is a big one. And if you can't, understanding the implications of those and simplify. I think scaling across regions is important. We saw that in the spatial simulation experiment. And so coming up with ways to better define those given the available data. Also non-representative tagging data or not meeting assumptions such as tags mixing is important consideration. Alternative approaches across broader continuums and relate back to the needs for spatial assessments. And this kind of the hybrid approach is one option for that. And I talked about using that hybrid approach in an integrated manner as well as a compendium of approaches working together. Building flexible dynamic workflows within operational frameworks. And then also countering the inevitable parameter expansion that we come with when we start expanding to space. Also trying to incorporate time varying processes. And there's a whole host of things that we can do in terms of things like random effects, parameter sharing, using spatial correlation to our advantage, and preference functions and things like that. The usefulness of using high resolution simulator, like the one we did for the spatial experiment, I think is really an important thing that we could come from this meeting from, recognizing that complexity is great, adding realism is great, but at the end of the day, we have to build models that are robust to some of these uncertainties and acknowledge the different hypotheses that remain, given we don't know exactly what the state of nature is. And then my final remark is that good practices, you know, when we think about it for tuna or other stocks in general, is less a destination, but rather an iterative developmental process. So my hope is that, you know, we learn and can collaborate either in meetings like this or through the literature and help develop more and more spatial models, test them through operating model structures to help build and help define what I think right now is a improving but still a little bit gray area for best practices for spatial modeling. And this is just a general consideration slide. I'm not going to speak to it. This was one of the conclusions from the more broad fall CAPAM in Rome, but I'll just leave that up for you to read at your leisure. Thanks.
Thanks, Aaron. We'll just go straight into the discussion period because there's no commenter for this topic, but feel free to either ask about questions about the presentation or just discussion topics in general. So has anyone got anything to start us off with? Dan?
Thanks, Aaron, for the presentation. Just think about that spatial experiment you talk about, right? The difference between the divergence between the, the operating model and the EMA. I think you briefly discussed some of the, the reasons. I mean, we haven't really explored that in a lot of detail in the meeting. I mean, talking about the, the difference between some of the processes between the EM and OM. Maybe another one is probably the information, the data being generated from the OM, put into the estimation model. I was just thinking from maybe the future perspective, when you design this kind of experiment, what do you think would be the general direction? Would be better in terms of testing the capacity of your estimation model? Would it be better to match those two a bit more closely, or is it better to more mimic what the reality is? Let those operating model and EM as separate as possible. Yeah, if you have any thought on this.
Yeah, thanks, Dan. I think we're learning as much about how to build a fine scale operating model as we are the estimation model. So I think that's one of the things that we're learning for sure, and we can carry forward. The other one I think is, I think we want to do several of the things that you mentioned in terms of having realistic mismatches, but also having cases where you get the result back that you expect. You learn from both. And I think one of the difficulties that falls on the side of building fine scale operating models like the one we did with SPM is there's a lot of complexities in that in and of itself. And so I think ideally what we would do is create several scenarios, different operating model scenarios, and then test some estimation models against it. That could be something that could be carried forward as next steps. We tried in this particular experiment, just because people so graciously were offering their analyst time, we just chose one. But yeah, that's a good point and something that would be good to do in the future.
Okay, thanks. Yeah, Nicholas?
Really neat looking over the or across the different software platforms. I'm curious, did you allow one group full freedom to sort of code whatever they wanted as far as an assessment model, where they were restricted to general software packages?
Yeah, there was a couple of folks who had more bespoke models. Zhikao and others built a spatio-temporal model, or that they used for crustaceans, and they had tried to adapt that for tuna. Not a ton of success so far, but there's plans to continue. And then there was a model called Spasm that was originally developed as a kind of a research simulator that was used. But outside of that, it was kind of, stock synthesis, Casal, multifan, etc. I think primarily that was done because building a spatial model is quite the endeavor, and folks were donating their time. And we basically asked them to build a 1-area model and a 4-area model. And if they had time, then they could explore alternative approaches. We haven't gotten there yet, but that's hopefully, again, something that, you build the model and then they'll come to use it and learn from it. So that's kind of where we're at.
Yeah, so related to that, the differences you found between the different packages, was that because people making decisions because of the limitations of the package, or was it just the assumptions they made?
That's a good question. I'm not sure I have the answer for that quite yet. We've got a whole bunch of information to sort through, responses from the analyst teams and things like this. This is, this workshop ended and then this one started, so we didn't have too much time to dive into all that. I suspect, though, Mark, that it's a little bit of both. But that's going to be one of the interesting parts that's going to go into the manuscript on decision points, is teasing that exact question out.
Okay. Any questions or comments or other topics to discuss about spatial stock assessment models? Is there anyone online? Because my computer crashed, so no. Okay, so I got a question about tag mixing, right? Tag mixing was a huge problem in Tuna's because of the sort of the location you can tag and basically the mixing rate and stuff like that. So was there anything from the spatial modeling workshop or the simulation analysis that suggested how we should deal with that?
Yeah, you're throwing the hard ones out there, aren't you? I don't know. I mean, there's at least one team, maybe several, that looked at several tag mixing specifications. And as expected, the results were a bit sensitive to that. Simon, do you remember anything in specific that was said? I think that the end result was that's an important thing to consider. And I think that's where we ended. A lot of discussion on it. And actually, there's several people in the audience who were part of that. So if there's something you remember that I'm not thinking of, please chime in.
Yeah, Dan?
Not really an answer, but my experience is that normally it's quite difficult to just use model diagnostics to sort of analyze tag mixing when you put a tag in a model. Normally this kind of thing is kind of analyzed outside of the model. I guess given the nature of the experiment, I don't think the team's really doing that sort of analysis, mostly just trying to testing the different mixing period within. And we know it's going to be, the model results are going to be sensitive to that.
And I guess that's something that we could look into more as part of a after experiment exploration of the results, to see in the operating model when tags actually were mixed and compare that with the performances of the different models with different mixing periods. Yeah, watch this space, I guess.
Yeah, Pamela?
It's possibly a minor point, but I'm a bit confused by your number 6, which says start with the most complex spatio-temporal structure and allow simplification, whereas I'm pretty sure elsewhere in your presentation and the way that most of the modelling teams approached it was to start simple and build up the complexity. Can you think of, I mean, they're both valid ways of doing things, I guess, what sorts of circumstances might you start simple, build complexity, and vice versa?
Yeah, thanks, Pamela, for pointing that out. I think what I was talking about during the presentation, starting simple and add complexity, is if you're developing the assessment model. I think the number 6 here is kind of more of thinking about next generation software. Think about everything that you would reasonably want to put in there, build that in and then simplify so that the modularity part of that can be easily conducive to, and I'm thinking like, you go to a CIE review or, a assessment review, and you try to justify a 3-region model, you likely have stepped through a 1 and 2 region, something like that. And oftentimes, if you don't have the ability to quickly change the data aggregation, the data inputs to fit that fundamental structure, just like switching from a seasonal model to a yearly model, you just don't have time to even do that. So the point here is to try to build that in so that we can have workflows that are conducive to those types of relatively quicker changes that help, with the assessment timelines that a lot of us are under.
I guess that's true from a practical point of view in terms of model building, and also from a model selection point of view. If you think about when you build a GLM, you can have forward selection going up to the more complex models, and backward selection starting with the most complex models and working back and finding what fits the data best. If you have something that's too complicated, you're going to get confounded parameters and models going to be over parameterized, and I think the same applies with a stock assessment model as with a GLM.
Thanks, Simon. Any other comments? Oh, Aaron, yeah.
Yeah, I got a question. When's the last time that somebody with a Tuna model has tried a Bayesian approach? I know Multifan did it, attempted it, and this was many years ago, and it took way too long. And I guess the reason I ask is, with improvements, we talk about improvements in methods and things like that, and particularly I'm thinking about the no U-turn, the nuts algorithm. I just think that even if a model run takes 40 hours in that context, you can learn so much in terms of diagnostics from fitting a Bayesian model, and then using some of the shiny app things that come through Stan in terms of diagnostics. I'm speaking because we do this for one of the assessments I conduct, and it is a fantastic tool to diagnose complexity, especially in terms of parameter performance. And some simulation work has showed that you're getting a 10-fold decrease in times when you use the no U-turn approach. So even if a Tuna model still takes forever, at least it's divided by 10 now.
Yeah, Juan Valero ran one for us when we did our risk analysis to compare the normal approximation with the posterior for one of the management quantities, just to see what the difference would be. If Juan's online, he might be able to tell us how long it took. I don't know if he is. I guess not. Yeah. So anyway, yeah, it was possible, I guess. I don't know what simplifications he may have made to make it work or anything like that, but yeah.
I think Jeremy and Craig might have run MCMC on the Castle 2 and Castle YFT models. I can't remember for sure.
Oh, okay, that'd be really good to know, because I think it'd be interesting to see, because we think of diagnostics in terms of complexity, and we have the list that I showed, but that's one that is underutilized for really complex models, at least so far. I think we'll be improving in the future.
Yeah, Pamela?
I was just going to say, it's not for Tuna, but we routinely do MCMCs for our New Zealand stock assessments, almost always, actually. And we can get, if you just do something simple like compare the medians of the posteriors with the MPD estimates, you can get quite big differences, and that's often a good diagnostic on its own, because it means you've probably got some kind of model misspecification, and we've actually used that to help figure out what that misspecification might have been.
Okay, Dan, you have a comment?
Yeah, just very quickly, I think I do remember some people have tried in the past, but most of the comments was that because the Tuna model tends to have lots of parameters and you've got very noisy size data, so some of the selectivity parameters, if you're doing MCMC, most likely run into boundary problems, and plus all the timing issues. And also these days, probably there's less incentive to do that because a lot of assessment move into using the, running the grid, and so there's less incentive to doing MCMC, I guess.
Okay, I got a question about spatial models. It's a little bit related to Tuna, but also more related, I guess, to more coastal stocks. But I know in some places, like in the east coast of the US, they do surveys in each state, and they don't overlap. They're not the same, but they're from the same stock, and we may or may not know where the boundaries are. I mean, our Tuna ones are a little bit like that with our fleets now, with the Japanese fleet contracting and the other distant water nation longliners filling in those holes, but also the areas where the purseaners are, often there's no longliners either. So how do we go about a spatial stock assessment model or areas fleet model or whatever model you want to deal with those types of data where they're spatially restricted on the same stock, maybe not even substocks, it might be a single interacting stock?
Yeah, that's another good question. I mean, I think in your example along states, coastal stocks, for example, one of the things you can do, like when you have surveys like that, is use your catchability as a measure across, scaling basically by state, like we do here in Tuna and regions. In some cases, the other thing that has been done coastal is use habitat survey maps to kind of as an indicator for habitat suitability, and link that back to, on a finer scale, to try to resolve some of those differences. For Tuna, longline versus purseine, or kind of that areas of the high seas or wherever where that's a bit more flashy, that's a good question. I would, actually my first thought came to Haikун's presentation on defining fleets in an areas as fleetest approach, because that could use some of those covariates to try to tease out what might be a good fleet structure as a implicit, capturing spatial dynamics. But yeah, it's be good to brainstorm about that.
Yeah, Paul.
Just one that we sort of battle with a little bit is this idea of scale, in regional scaling that you mentioned before, and we tend to make these assumptions that we have a gear type that has the same selectivity, etc., across the whole of the range, and that provides us information on regional scale. If we can't make those assumptions, and then we don't have an index that's relatively comparable among our spatial regions, should we still try to do spatial assessment without that information?
Yeah, I mean, I think you still want to look at maybe why the regional scaling is not potentially working. If it's CPUE, for example. There also might be things like other approaches along this continuum I was thinking about, like a spatiotemporal model that uses covariates, sea surface temperature, I don't know, whatever, that is perhaps determined not to be used directly in the assessment model, but as a supplement to help inform what those regional scalars are. Another one is, I think, ecosystem models, for you guys like the CAPAM and Atlantis, and then there's others that I think can help. It's probably not going to give the answer, but it might at least show, you're in the ballpark or something's wrong. We need to look further into that. I think the regional scaling has something to do with what we're seeing in the simulation project, but I'm not convinced at this point that that's a across-the-board artifact. I think what we need to do is what Dan suggested, is look at a couple of other operating models, because I think there might be, in the particular operating model, we have a disconnect between where fishing effort and F in each area isn't directly proportional to biomass. So you're getting that bias picture, which is still useful because that certainly can happen. But to add a couple of other scenarios, I think would be useful to really nail down in a simulation context when you can get that wrong, when you may not, and when it's robust to getting it wrong.
Yeah, thanks. Any other comments? Nicholas, I know you have a fine scale operating model, and unlike your one, which basically takes the effort from where it actually occurred, Nicholas has rules on how the fishermen, where the fishermen go fishing, and depending on the catch rates and the closeness to ports. Do you want to tell us how that works on yours?
As options as to the theoretical relationship of where you fish. And so the two options I've used most often are a gravity model where effort's attracted to cells of high abundance and detracted from cells that are far away from a port. And then, as you mentioned, to have situations where you can correctly test an estimation model. I also have a situation where you allow for just random fishing over space, so that a spatially aggregated assessment could be correctly specified. And that's proved super informative. But I couldn't agree more with the fine scale, spatially explicit simulation framework to test some of our models.
Great, thanks. Matt Vincent is online with a question.
Yeah, I wanted to ask Dan about his thoughts regarding selectivity and whether, so in a spatial model, a lot of times, well, I guess in a simplistic model or the Fleets' area model, we often allow selectivity to be very flexible to allow for the differences in the area essentially that we're trying to model. But when we move to this spatially explicit model, I guess a lot of times we'll share selectivity among similar population, or similar fleets, sorry, because we often think that we want the movement to be driven by the selectivity or the link composition observed in the data. But then there's also the issue of we might have spatially varying growth or whatever. And so I guess that it's a question we've often struggled with, is whether selectivity among a fleet should be constant across the different regions, or whether you make an assumption that they're all separate between all the different regions or somewhere in between. And I'm curious what your thoughts on that are.
That was directed to Dan. I'm guessing it's Dan Fu.
No, sorry, Aaron.
Aaron.
Yeah, well, Matt, you said Dan at the beginning, so I didn't pay attention. No, just kidding. I think, I mean, I'd actually like to see some more work done on exactly what you're talking about there. I think, from a purist standpoint, if you were using movement to try to monitor where fish are, and then you have selectivity, right? You're really only kind of looking at the gear contact component of that. Now, if you take away movement away, and then your selectivity now is gear contact and availability, it's you know, right, it's attempting to absorb and take into account availability. And then if you have both, so you have selectivity where you're trying to take into account availability, but you're also estimating movement, maybe when you don't have perfect information. I think those three would make for an excellent simulation experiment. So I'm not answering your question, I'm just adding more work for somebody.
Yeah, Simon?
Yeah, I agree with Matt on this. This is a really tricky one. But I had a point on this in my presentation on size data. I think obviously if you've got areas as fleets, you need to have different selectivity everywhere. If you've got regional scaling, then like you're saying, if availability comes into it, then availability is going to be different between areas. And if you need to have time varying selectivity to account for that temporal variation in availability, then you can't have the same selectivity in every region. Otherwise, because you can't, it's different in every region, obviously. In terms of the motivation for having the same selectivity everywhere, the size data is never going to be informative enough to tell you where fish are moving, and if you try to do that, then you're going to get an answer, but it's very unlikely to be the right answer. And yeah, so I generally think it's probably better not to keep them the same, but I agree a simulation is needed to test it out.
Yeah, especially because, you know, the comments earlier about selectivity and growth, you've got other things that can absorb some of that, as well as recruitment, if you have recruitment apportionment, or even stock recruit, you know, meta population with individual stock recruit curves. So simulation would be good because you can turn one off at a time, yeah.
Okay. Any other comments? No. Yeah, Nicholas.
Curious as to how blind were the assessment teams? Like, were they given maturity OGIs or growth OGIs, or how did you go about that?
Yeah, for this particular one, well, I'll probably point you to the GitHub site because it's got the list of everything, but they were given quite a lot, but they weren't given some of the key things like movement and things like that. So they're given R0, the mature, all the biology was perfect. And we really wrestled with this from a design standpoint from the beginning, because we wanted folks to complete the project, right, and make it doable, but also focus on some of the axes of a lot of action, movement, recruitment, things like that. So we did give the folks quite a bit, but yeah.
Yeah, thanks, Aaron. I guess we probably should finish up the discussion pretty soon. I just wanted to point out one thing during the workshop that I thought was pretty cool was the areas as fleet diagnostic, where you would, you know, in the areas in fleet approach, you basically create a single index over the whole area, doing the spatial weighting with CPUE and stuff like that for the length comps and everything, and for the index. And then actually creating a single index for each of the areas as well, not fitting to it in the model, but seeing how well the model fits to see if there was actually differences in local depletion that couldn't be explained by selectivity. Yeah, I thought that was pretty good. Okay, well, thanks everyone, and I think we'll move on to the next topic, which I think is me. Okay, yeah, so I jumped in to fill a position for selectivity, so I apologize if the presentation's a little bit rough, but I put this together with Kevin Piner, who's done a lot of work on Tunas, and most of you probably know him. And so to start off, I just want to mention that you can't really look at selectivity on its own. There's a lot of things in integrated assessment that it gets confounded with, and some of the big ones are the length composition, sampling, and the quality of that, and then their sample sizes. Then the data weighting too, and also fishery definitions, particularly if you're going in as areas as fleets type approach. So that will come up throughout the presentation, and also in the presentations we've already seen, like just the previous one was talking about selectivity. So the first thing is just to flick through the different historical approaches that have been used for stock assessments and what they've implied for selectivity. Some of the initial yield per recruit stuff was just basically looking at what the optimal age at entry into the fishery was. So that's kind of looking at selectivity in a sort of a knife edge type selectivity curve. Surplus production models, they don't have a defined selectivity. It's kind of a little bit hard to understand because you have vulnerable biomass and spawning biomass being the same. And a lot of fisheries, like in the tunas, the purse seine catches a small fish and the longline catches a large fish. So it doesn't make sense that they're being treated the same in a surplus production model. Cohort analysis typically will be used one fishery, so all of the different gear types are combined together. You're using age data, and you're assuming no sampling error. But in those, the selectivity is very free. So it's time varying and flexible across age with maybe a couple of constraints on the maximum age or something like that. And then finally, when we move to the more statistical approaches, we typically had the separability assumption, which assumes that the selectivity is time invariant. Often we moved into multiple fisheries to try and model the differences in selectivity among fisheries. And one of the other big things on this is we were fitting a lot to link frequency data, and that's part of the reason to move to that approach over the cohort analysis approach to take into consider sampling error and things like that. Okay, next thing is the importance of selectivity. And the real main issue we have is basically fitting to composition data. And that's because the composition data provides information on absolute abundance. And if you get the selectivity wrong, plus a few other processes as well, you can actually bias your absolute biomass estimates and also your trends over time. The second thing it's used for is removing fish at the right size or age. And that's really important in our tuna fisheries because we've got purse seine, well, at least the tropical tunas anyway, we've got purse seines that catch on floating objects that catch small fish, and then longliners that catch large fish. And so we have to make sure that we're representing the right selectivity to remove the fish at the right size. And then finally, it's also used to calculate management quantities. And so if you have a fishery that's all longliners, then you get a really high MSY and you usually get a high BMSY to B0. But if you take the purse seine fisheries, you end up getting a low MSY and a low BMSY to B0. So very important for calculating management quantities. So we have to get it right. Okay, so this here sort of gives an outline of one way to think about how you specify selectivity. So if the fishery that you're representing, so this is assuming you've defined your fisheries. If the fishery that you're looking at catches a lot of fish, then you probably have to get the selectivity right to make sure that you're taking the fish out at the right size, because that might make a difference. And it will definitely make a difference for MSY calculations since it's the majority of the catch. It also probably informs recruitment if you think about a cohort analysis, because it's most of the catch, it represents most of the fish that have been removed, so therefore it will relate somehow to the estimates of recruitment. Now, if the fishery only catches a small amount of catch, it really doesn't matter that much if you remove the fish at the wrong size. So you really only need to approximate the selectivity curve. If it's an index or a survey, then you really have to get the selectivity right. And the reason for that is, first of all, is because you want to make sure it's representing the right component of the population. because hopefully your survey is driving your estimates of relative abundance and also possibly absolute abundance. But also often you might want to use the survey composition data to provide additional information on absolute abundance, abundance trends, and recruitment. One caveat to this is that if you have reliable length comps and high sample size, even for a fishery that has small catch, if it's representative of that population, then you might actually want to use that to provide information about the population processes such as abundance trends, recruitment, and absolute abundance. Right. So the first thing you want to do, this is assuming you've defined your population structure, is to define the fisheries. So obviously different gears typically catch different size fish, so you want to do that to start with. And the main reason to do this is to reduce the temporal variation in selectivity. Yeah, there's a pre-recorded presentation a bit about making sure that you're using different selectivities for different gears on the website by Cole Carano. Then use the areas as fleets approach to represent the spatial structure when a spatial model is not feasible, and also to represent seasonal movements in the same situation. And this can be done by using regression tree analysis, like Haikun was presenting in the spatial workshop in the previous days, or some other clustering method, preferably one that's flexible and can create non-regular contiguous clusters. And in that, you want to include things like season, area, latitude, longitude, possibly other factors like Carolina was talking about in terms of things that would define fisheries. There'll be a trade-off between the number of fleets that you define in this and how much temporal variability and fleet selectivity is needed. If most of the temporal variability in selectivity or link frequencies is due to spatial considerations, then the more spatial structure you have in your fisheries, the less likely that those selectivities are going to change over time. So the next main concept that we have to talk about is functional form. First of all, think of whether or not the selectivity is age or length selection, and that really depends on the processes controlling selectivity, which I'll talk about later. So the first is functional form. Often we'll use the double normal or some kind of variation of that, or a logistic if we're doing asymptotic selectivity. The problem with this is it's very limited in the shapes it can take. Something that's more flexible are splines, which several packages use. I personally find them difficult to parameterize. You're typically not estimating a smoothness parameter, you're just fixing that, so it's quite a lot of arbitrariness in it, and you get some weird curves. Then there's more non-parametric or semi-parametric approaches, and these ones are quite flexible, but again, you should be estimating a smoothness parameter, which is difficult again unless you're doing random effects type modeling. The next major concept is temporal variability, and so having time varying parameters. You can have time varying, you can have it on the parameters of a distribution, and so you can either do it in time blocks, but there you have to choose the number of time blocks and you've got to choose the time. You could do a random walk, which requires quite a few parameters, and if you're not doing a random effects approach, again, it's difficult to determine the smoothness parameters. You could also do deviates around a distribution, so this is the semi-parametric approach. This could be age and time correlations, like Haikon's done in a couple of his papers, or you could be using a random walk like implemented in Anders' SAM package. And again, as I mentioned before, do you want to do more fisheries or you want to model time varying selectivity? The next one is age versus length. And this is actually quite important. We've seen this in a few tuna assessments where choosing age selectivity has caused some issues. So multi-fan CL can only do age selectivity. So it makes it difficult to estimate length frequencies of the small fish. So for considering this, you want to think about the processes that are involved in selectivity or availability. So for length, it's processes typically like the characteristics of the gear, like the mesh size, hook size, things like that. One limitation of the length-based methods, if you're using sort of non-parametric type selectivity curves or time-varying selectivity, because you've got a lot of length bins, the length-based selectivity has a lot of parameters, and you mightn't be able to do that. It might be computationally impossible. And then for age, it might be ontogenetic movement. Another thing to consider is that length doesn't change much for old individuals. For using age-specific selectivity for old individuals, even though the processes are length-based, it might actually be still okay, especially if you're trying to do time varying and you want to have fewer parameters. But typically what we see with age-based selectivity is you can't fit the length distributions of the young fish because it is a length-based process and the age selectivity just doesn't allow that. Yeah, in tuna, the couple of things that you might want to consider is what is movement? Is it gradual movement of time? Is it seasonal? How does it operate, and how do you represent it with selectivity? It may be length or age-based, who knows? There's some weird stuff that goes on with tunas, like attraction to fads. I mean, what's causing that? Is an age-based process or a length-based process? Does the swim bladder develop based on age or length? In the Indian Ocean, they have small fish and big fish in the unassociated sets, and we don't really know why that happens. Is that age-based or length-based? Okay, next one, sex-specific in tunas, like we heard with Lisa's presentation, that we're having evidence now that we are collecting evidence that suggests that growth is sex-specific, but we don't really have a lot of sex-specific information. And so how do we deal with selectivity when we don't have that data? We can assume that selectivity is the same between males and females at age or at size, but then the opposite selectivity is different. And then, or do we somehow share it between fisheries so that the offset between males and females is the same as a fishery that has length competition data? Okay, so one thing that I've been thinking about is really we should be defining fisheries so that the selectivity curves and the length frequency curves are pretty regular. So basically, if you don't get something that looks like a double normal, you're probably adding a couple of fisheries together or a couple of areas together that different have size fish. So if you get fisheries that have like long shoulders like this, I mean, so, yeah, length frequency distributions or selectivities that have long shoulders like this, you have double modes, or the selectivity has some weird kink in it. It's probably because you're adding two fisheries or two types of fishing methods or behaviors or areas together that you probably shouldn't be. So you should be further splitting fisheries. So that suggests you could go back to the double normal as your selectivity curve rather than doing splines and things like that. It's a little different when you're talking about a fishery versus an index. And when we do our CPUE standardization, we should never use the same selectivity for the index and for the catch. There may be cases where it's probably approximately okay, but it kind of doesn't make sense because the catch, the fishery should be representing the removals and the CPUE should be representing the population. And so we should be doing this index approach where we do the whole area, spatially weight the comps by CPUE, and then possibly, if we can, use an asymptotic time invariant selectivity for the index. So basically, we're trying to set up a survey with our CPUE index. May not always be possible, but in the fisheries, we should be using areas as fleets, spatially weight the comps by catch, and then maybe a time varying flexible dome shape selectivity, but I'm starting to think that maybe a double normal time varying selectivity might be the way to go. As far as model fitting goes, my sort of current thinking on the approach is to estimate the composition effective sample size outside the stock assessment to represent the sampling variation. Any additional variation that you estimate, say through the Francis or the Dirichlet likelihoods, is due to model misspecification or unmodeled process variation. You probably can't fix every single piece of misspecification, but if you fix most of them, then this kind of weighting hopefully would be okay. And then look at the empirical selectivity diagnostic to identify selectivity misspecification. And so that just gives you an example of that diagnostic. Okay, so as far as what research we need to do, actually didn't fill this out much, but there's a couple of things I thought of while I was doing it. One is, for fishery definitions, the approach that Clarity put together is pretty cool, but it really needs a lot more work, and it needs a method that creates irregular clusters rather than just latitude and longitude. Of course, contiguous spatial areas would be needed to do that. We want to remove the recruitment effect, because that's going to go into the link frequency distributions. And we have a method for doing that, but I'm not sure if it's any good. And then also possibly allow for other covariates to define the fisheries, like environment, if we want to have time varying definitions for our spatial fisheries. And I'm not sure if we need this anymore, but because I said we need double normal selectivities. But anyway, I think there would be a good case for developing efficient, flexible, time-varying length-based selectivity with inestimable smoothness parameters. Something a little bit easier for me to understand than a spline. Okay, and I'll just leave this up for you to look at. I'm not going to go through it. But that's my preliminary best practices, and there's probably a few things in there I disagree with already. So just to give you some ideas, and I think we might have time. Oh, yes, we do. We have quite a bit of time for questions. So anyone has questions on my talk? We're going to have a comment by Dan after the break, and then a discussion period. So Dan has a question.
Presentation. About that practice of separating the catch and the index selectivity, I know you kind of strongly support it. I don't. Do you think that idea has been around very long? And do you think is that something for you? You think it should be done for the assessment in general, or is just for the tuna assessment? In IATTC, we haven't done that. I mean, our index selectivity still links to the fishery selectivity. But I do find it's just make it impossible to try to do time variant selectivity on the fisheries, because that just messed up your fits to overfitting your CPV. I don't know if any. I believe there's still a lot of assessment that doing things that in such way, right? Linking those two. Yeah. I don't know if there are any cases where people are doing that, but in the meantime is able to do in time variant selectivity for this.
Yeah. So I guess by default, I think this is what you should do, right? Back when I started doing fisheries, we would have areas as fleets. We would have a different index for each fleet, which was each area, but they weren't representing different subpopulations or anything like that. So that meant that you'd have an index going up, an index going down for the same population, and it wasn't explainable just through the selectivity. So I think that that should be the default. If you find that you can't run the models if you do that or something, then maybe you need to share selectivity somehow, but I don't see a reason why. The only way it would happen is if you created an areas as fleet approach where one of the fleets had such low length frequency samples that you couldn't estimate its selectivity. And then you would probably want to share that selectivity with another fleet or with the index and remove the length comp data for that fleet. Yeah, Nicholas?
Yeah, just curious, which method would you recommend for estimating the effective sample size outside of the assessment?
Outside of the assessment? Yeah, I never really done it myself, so that's why it's easy for me to recommend it. Yeah, so there's bootstrap approaches. I know Nick Davies did one a long time ago for Snapper in New Zealand. And I know Vast produces something which Haikun is used. I'm not sure if the Vast method is actually something you should put as an absolute sample size. I know we've used it as a relative one, but I'm not 100% sure if it's actually a good measure of the actual sampling variability. I mean, it might be, but I just don't know. So, but yeah, I recommend that someone develop a really cool method for doing that. That's, you know, accurate and, you know, precise and non-biased and whatever. Yeah, Aaron.
Yeah, thanks, Mark. Jimmy Anelli is online. He's got to put a question in the chat, so I'm just going to read it since I see you can't see it up there. He asked, you mentioned the lack of fit for smaller size fish due to age-based selectivity, but how can you know that it's not due to growth being too rigidly defined, especially for young fish, which may have a large variability in growth rate and distribution in length at age?
Yeah, good question, Jim. I'll let Dan answer that in his presentation. I think he's going to cover something related, so we'll wait till then. I mean, one thing related to that, it's not related to what Dan's going to present, but often in length comp distributions, you actually see a couple of little fish somewhere, and only in some years, and that really messes you up because you've got a really low selectivity for seeing those fish, and then they pop up, and of course that has a high leverage on your selectivity curve, which can cause problems. And so you should be looking for those and adjusting the analysis in some way to deal with them. One way is to do in your composition data having binning, so you know, accumulate all the small fish or something like that. A better way probably is just to delete them from the data set, because they're either or often they're data entry errors, or they may be, if it's like a recreational fishery with a size limit or something, it's someone caught the wrong size fish and they still reported them and stuff like that. So they're not really important to the overall assessment, but they can cause some problems in your modeling. Yeah. So Arnie.
Yeah, thank you. Yeah, sorry, green curry. Yeah, sorry, just for broader context of selectivities, I think it's worth bringing up the by now probably the most common approach in European stock assessments, which is using state-space models with single fisheries, so quite an aggregated entity, but with great flexibility and full time variation thanks to the state space parameterization. So yeah, they lose some obvious resolution by aggregating everything, but they get the time variability, and at least for their data sets, you know, where they have pretty high quality H compositions, it seems to be a reasonable way to go.
Yeah, so this is like Anders' approach, and we talked a little bit about that in Rome, and they've also got, I think, is it Tobias or Casper? I think it might be Casper, has a paper showing that in at least one case that doing that rather than having multiple fisheries was just as good, I think. There is a few problems there. One is, like for tunas, we have really small fish in the percent and really big fish in the long line. So probably not a good idea. But, you know, Anders's approach could be used for 2 fisheries easily. So, you know, I don't think we want to dismiss the state space, you know, time varying selectivity approach just because they use 1 fishery, because it's easy to expand, and I think they've done that. The other thing is when you go back in time. So when you don't have any comp data, right? So, you know, a lot of fisheries have a long history of comp data, but there are a lot of fisheries that only have recent comp data, even in Europe. And so you're making up a whole lot of stuff, and whether or not, and so you've only got 1 fishery, right? And you've got 1 set of comp data. So when you go back where there's no comp data for a particular fishery, what do you use, right? If you're just using the comp data you've got, obviously you're misrepresenting the fish that are being removed from the population. And it's unclear to me at what level you would actually get some bias by doing that. So I think it's much better to divide out the fisheries, at least by gear, and have time varying selectivity for each of those fisheries, as long as the model is computationally possible to converge and things like that. Yeah, Carolina?
I was wondering, similarly to the indices of abundance, like the knowledge of changes in technology or strategies could help us inform at least blocks in selectivity. And then there will make the case for us to invest into doing this cataloging and learning about these changes at least.
Yeah, I think a lot of people have taken that approach, and I think Haikon mentioned it. I don't know if, I guess it was, I don't know if it was, it must have been in the spatial modeling workshop, that, you know, doing the time varying selectivity is pretty computationally intensive, and so time blocks are probably good enough in a lot of cases. And so maybe that identifying major time blocks through changes in gear technology might be a good idea. And if you're doing a random effects approach with lots of flexibility, you know, having a couple of time blocks instead is probably not adding more variability than that. So you're not probably going to lose a lot of information. Yeah, but I think we might as well break for coffee. We don't answer all the questions before Dan's talk. We might cover his presentation, so we better stop. Thanks.